am. And I will try. Sometimes I can't get it to upload, but I should be able to. I hope I will.
All right, Professor.
Someone had a question for which problem? Which section or which
Number
problem?
29
Which
for
section?
section 8.2.
8.2, number 29. So that's x cubed sine x?
Yeah.
Okay. So we have x cubed sine x dx. And if you're going to integrate by parts, a natural thing to try is if you let u equal x cubed, because then when you differentiate it, the power is smaller, is lower, the degree. It goes from x cubed to 3x squared. So I make dv dx be sine x, and this is minus cosine x. So this is my u, and this is my v. And these are the derivatives. So by the integration by parts rule, this is minus x cubed cosine x minus the integral this way, which is minus 3x squared times minus cosine x, makes that a plus cosine x dx. So I haven't finished the work, but what I did is I started with this integral, which had x cubed, and this integral just has x squared. So I can try to compute this integral and then plug the answer back in here. So suppose I want to find the integral of x squared cosine x dx. Again, I would want to make u equal to x squared, so du dx is 2x. If I let the derivative of v be the cosine, then v is the sine. So by the integration by parts rule, this is x squared sine x minus the integral of these two, 2x sine x dx. So I've reduced now an integral from where you have x cubed to x squared to x. I have to use integration by parts a third time to calculate the integral of x sine x dx. So if I let u equal x, the derivative is 1. If I let v equal sine x, the dv dx equals sine x, the integral of that is minus cosine x. So this equals minus x cosine x minus the integral of this, minus makes this plus cosine x dx, which is minus x cosine x plus sine x plus a constant. So now I figured out what the integral of x sine x is. I can plug that in here. This is x squared sine x minus 2 times the integral. So minus 2 times this is plus 2x cosine x minus 2 sine x. And now I know what this is. I can plug it in here. I get minus x cubed cosine x plus 3 times this, 3x squared sine x plus 6x cosine x minus 6 sine x plus a constant. So I had to do integration by parts 3 times to get the answer, but you persist and you keep going, and at each step you get an integral that's slightly easier than the one you started with, and eventually you get to something simple like the integral of the cosine that we know is the sine.
Okay.
That's how you do it.
Could we also go over number 13?
In the same section?
Yeah.
Okay. So that's going to be very similar. You're going to have to integrate by parts probably 3 times. Let's see. So 8.2, number 13. This is the integral of x cubed e to the x dx. So I'll let u be x cubed and dv dx be e to the x. The derivative of x cubed is 3x squared. The integral of e to the x is e to the x. So this is x cubed e to the x minus the integral this way, minus 3 the integral of x squared e to the x dx. So we need to do this integral. So again, let u be x squared and dv dx be e to the x. Then this is 2x and this is e to the x. So this is x squared e to the x minus this integral, 2 times the integral of x e to the x dx. So we've reduced it to this. We have to find the integral of x e to the x dx. X e to the x, 1 e to the x. This is x e to the x minus the integral of e to the x, which is x e to the x minus e to the x. So that's what you plug into here. This is equal to x squared e to the x minus 2 times this. So minus 2x e to the x plus 2 e to the x. That's the integral of x squared e to the x. So you take this and you plug it back in here. You get x cubed e to the x minus 3 times this, minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus a constant. And if I did the arithmetic correctly, if you differentiate this, you have a lot of cancellation, and this is what you end up with. So the point is, with integration by parts, you don't necessarily solve a problem in one step. Sometimes you have to iterate. You integrate, you use integration by parts applied to an integral, and it gives you another integral, which is in some sense a little bit easier. And you keep going and you hope you get a succession of easier integrals until you finally get one that you can just do.
Professor,
Yeah,
so the integration by part is gonna be part of the exam tomorrow?
yes,
Oh, I thought it was just gonna be from lesson 1 to 8.
no.
Oh, okay.
I said the syllabus, the departmental syllabus covers a 15-week semester. There are two midterms plus a final. And I said from the beginning, we have one midterm in the middle of the course. And if it's in the middle of the course, it has to cover half the material. And that's
Okay.
what's on the review sheet as well.
Thank you, Professor.
Oh, yeah, Professor, you talked about that exam's gonna be open book. How?
I'm sorry, your voice faded away there and I did not hear you.
Okay, yeah, Professor, you say that the exam's gonna be an open book. What do you mean
Yes.
by the open book? Is it the question gonna be from the book or?
No, the question, it just means if you need to use the book, you can use the book. That's all.
Copy.
Professor, could we go back a few chapters back to 8.1?
Section 8.1. Chapter 8,
8.1.
Section 1.
No, just 8.1 and problem number 9.
Before we go back,
what
Professor,
section?
8.1.
So chapter 8, section 1.
Yeah.
Which
sorry.
problem?
Number 9.
Number 9 is 3 over the square root of 1 minus t squared.
Yes.
Okay.
Professor, before
Yes.
we go on to the next problem, could you just explain how you moved the 2, like how you got x squared e of x minus 2x e of x plus 2 e of x? Where'd you get the 2?
Are you looking at this?
Yeah.
So I have here I'm integrating this, x squared e to the x. The derivative of x squared is 2x. The integral of e to the x is e to the x. So by integration by parts, the integral of x squared e to the x is this times this, x squared e to the x, minus this minus the integral of this times this. So this is 2x e to the x. I just took the 2 outside the integration sign.
Oh, okay, okay, and then you distribute. Okay.
Okay. So you asked about 8.1. Number 9, which is the integral of 3 over the square root of 1 minus t squared dt. And the 3 is just a constant. I can take it outside the integration sign. And we want to know what is the integral or the antiderivative of the square root of 1 minus t squared. So this just comes directly from an integration formula from last semester. The derivative of arc sine of t is 1 over the square root of 1 minus t squared. So this is just 3 arc sine of t plus a constant. And this is just one of the formulas which you're supposed to know.
Okay, thanks.
Could we go over section 8.3, number 5?
8.3, number 5. So that's the integral of cosine to the 5th x sine x dx. Is that the problem?
Minus cosine to the 3rd. But I mean, I guess it's the same principle anyway, so it's fine.
Okay. Well, again, you just make a substitution. You see you have sine x dx. If you let u equal cosine x, du is minus sine x dx. The derivative of the cosine is minus the sine. So if you substitute, this becomes u to the 5th minus du, which is minus 1/6 u to the 6th. So you get minus 1/6, the 6th power of the cosine. U is cosine x plus a constant. So that's just a straightforward substitution.
Oh, okay, I see. Thank you.
Let me do problem 6, because that's one there's one slight technique you have to use there, which we didn't have to use just now. That's the integral of cosine cubed x sine to the fourth x dx. So when you have a power of a cosine and a times a power of a sine, you look to see whether at least one of them is an odd power. So 3 is odd. So I can write this as cosine squared x sine to the fourth x cosine x dx, because cosine squared times cosine is cosine cubed. And then I use the identity that cosine squared is 1 minus sine squared. And now if I make the substitution, u equals sine x, so du is cosine x dx, this becomes just 1 minus u squared times u to the fourth du, which is u to the fourth minus u to the sixth. Which is 1/5 u to the fifth minus 1/7 u to the seventh. So this is 1/5 fifth power of the sine minus 1/7 seventh power of the sine plus a constant. So if you have an odd power, you strip off one of them. So you have an even power times the cosine, and you use this identity to write everything in terms of the sine. And then this substitution simplifies everything immediately.
Wait, how'd you get the substitution to be just sine of x? Shouldn't it be sine squared of x?
No, if you let u equal sine squared of x, the derivative is going to be much more and it probably won't work. I mean, you can try it. If it works, it works. This works. Now, with every problem in mathematics, there's usually different ways to solve it. So this is one way that solves it. And if you can find another way, that's okay. But what we need is the answer. And how you get the answer is up to you.
I mean, like, what I mean is, like, you see how the new integral that you have was 1 minus sine squared of x multiplied by sine to the fourth of x? And then
Right.
I just wanted to know where you got just the sine x from.
Well, so
Because it's
if I
not
look at
really-
this whole expression, it's some expression involving the sines. And here is cosine x dx, which is the derivative of the sine. So I know that if I let u equal sine x, I know this will simplify. Now, if I made u equal to sine squared x, then du would be 2 sine x cosine x, and it just wouldn't work. I mean,
I get it.
I mean,
Mhm.
it's not like there are rules about these things. It's like a skill. It's like painting a picture of something. You know, it's not like a rule how you paint a picture. You develop techniques for doing it. So here you develop a technique for doing these integrals, or multiple techniques. If you try u equals sine squared x, it's a perfectly reasonable thing to try. You try it and you will see it doesn't work. So you have two choices. You can give up or try something else. I suggest you try something else. And this one does work.
All right, thank you.
Other questions? Well, let me do something involving partial fractions, because that's the final technique in integration that is in the course and that we cover on this midterm. So partial fractions is section 8.5. So in section 8.5, there's several homework problems and a couple of problems on the review sheet, which are just supplements to the homework problems. So let's say 8.5, number 7. So this is the integral of 1 over x squared minus 9 dx. So we can factor x squared minus 9. It's x minus 3 times x plus 3. So the theorem about partial fractions says we can write 1 over x squared minus 9 in the form a over x minus 3 plus b over x plus 3 for some numbers a and b. So we have to find the numbers a and b. But this is the theorem about partial fractions. It's an algebra theorem. And one way to do this is just to put this back over a common denominator. If you multiply a by x plus 3, I'll have x minus 3x plus 3 is the common denominator, plus b times x minus 3. So if this fraction equals this fraction, the denominators are the same. This is just x squared minus 9. So the numerators have to be the same. You have a times x plus 3 plus b times x minus 3 has to equal 1. And we need to find a and b. So there are two methods I'll show you to do that. One is we just write this as, this is a plus b times x plus 3 times a minus b. That's the right-hand side, ax plus bx, 3a minus 3b. That equals 1. Or as a linear polynomial, this is really 0 times x plus 1. So this coefficient of x has to be 0, and the constant term has to be 1. So we have a plus b equals 0. So b is equal to minus a. And 1 is 3 times a minus b. But b is minus a, so that's 3 times a plus a, which is 6a. So that means a is 1/6, and b is minus a is minus 1/6. So with the first method, we get these numbers. The second method is just to stick with this equation. If we let x equal if we let x equal 3, this is 0. We get a times 3 plus 3, 6a, plus 0 equals 1. So a is a 1/6. And if you let x equal negative 3, this is 0 times a minus 3b, sorry, minus 6b, minus 3 is 1. So b is minus a 6. So both ways give the same answer, of course. The point is just that there are two different ways to do this. So this expression, 1 over x squared minus 3, this is equal to the integral of a, that's 1/6 over x minus 3, plus b, which is minus a sixth, the integral of 1 over x plus 3. So this is just gives us two logarithms. This is 1/6 the log of x minus 3 minus 1/6 the log of x plus 3. And if we want, we could write this as just the log of the quotient, x minus 3 over x plus 3. But this form is correct and this form is correct.
Could we go over the two methods again?
Yeah. So I know by the formula for partial fractions, x squared minus 9 factors into x minus 3x plus 3. So 1 over x squared minus 9 can be written as a sum of these two simple fractions, some constant a over x minus 3 and a constant b over x plus 3. And if I put this over a common denominator, I get a times x plus 3 plus b times x minus 3 over this, which is the same as x squared minus 9. So these two fractions are equal. They have the same denominator, so they have to have the same numerator. So we get this equation, a times x plus 3 plus b times x minus 3, that's equal to 1 for all x. Now I need to find a and b. One way I can do it is, I notice if I let x equal 3, this term is 0. So I just get 6a equals 1, where a is a sixth. And if I choose x equal to minus 3, this term is 0. I get minus 6b is 1. So b is minus a sixth. That's the simplest way to do it. This is usually the easier of the two ways. Here, I just took this expression, collected the terms. It's a linear function where the coefficient of x is a plus b. The constant term is 3 times a minus b. That's equal to 1. So the constant term is 1, and this coefficient has to be 0. And I solved the equations.
The only part that I'm confused of now is that, okay, I get that we have to, you can set it either to x equal 3 or negative 3. So either a or b, it just becomes either 0 and then 6. But then how does that lead to 1 over 6?
Well, so here's this equation. If I plug in x equal to 3, this says, let x equal 3. If x is 3, 3 plus 3 is 6. This is 6a. 3 minus 3 is 0. This is 0, equals 1. So 6a equals 1. So a is a sixth.
Oh, okay. Okay, thank you.
Let me do another one of these. These are interesting. This is 8.5, let's say number 11. Number 11, we have the integral of 5 minus x over 2x squared plus x minus 1 dx. And the first thing is to check the degree of the denominator is smaller than the degree of the numerator is smaller than the degree of the denominator. If that were not the case, we would have to do long division. But this has degree 1, this has degree 2, so we're okay. then we need to factor the denominator. So I think this factors into x plus 1 times 2x minus 1. What happens if you can't factor it? Then you can't do the problem, right? I mean, you have to be able to factor. So the theorem on partial fractions says that this fraction, this rational function, can be written in the form a over x plus 1 plus b over 2x minus 1 for some a and b. Again, we cross multiply a times 2x minus 1 plus b times x plus 1 over x plus 1, 2x minus 1 equals this. So the denominators are the same, so the numerators have to be the same. 5 minus x is equal to a times 2x minus 1 plus b times x plus 1. And this is true for all x. So if we make good choices for x, we can probably compute a and b quickly. For example, I see from this that if I let x equal minus 1, this is going to be 0. If I let x equal minus 1, I have 5 minus minus 1, which is 6, is equal to a times 2 times minus 1 plus b times minus 1 plus 1. So 6 is, this is minus 2, this is minus 3a, and this is 0. So 6 is minus 3a, a is minus 2. Well, I just found a. I look at this, if I let x equal to a half, this becomes 0. So if I let x equal a half, 5 minus a half, which is 4.5 or 9 halves, is equal to 0 plus b times a half plus 1, which is 3 halves b. So if 3 halves b equals 9 halves, that means b is equal to 3. So if I did this arithmetic correctly, this expression, what I'm integrating, is very simple. It's minus 2 over x plus 1 plus 3 over 2x minus 1. So this is minus 2, the integral of dx over x plus 1, plus 3 times the integral of dx over 2x minus 1. Let me factor out a 2, x minus a half. Now this is just minus 2 times the log of x plus 1 plus 3 halves times the log of x minus a half. And I'm done.
So is it safe to say that when we're finding for A or B, it would be best to try to get one to go to 0, like try to get a number, like trying to get one of the letters to equal 0, so it would just make it easier?
Yeah, that's always the first thing to try. Now, that will always give you useful information. Sometimes it's not enough, and then and then you might have to pick some other number. You just pick some random small number, and you end up getting some equations in A and B and C or whatever are the constants, linear equations, which you can solve from high school algebra. Well, since these are fun, let me do another one with partial fractions. So the integral, this is number 21. X squared minus 1 over x cubed plus x dx. So again, you look at the degrees of the numerator and denominator. Degree 2 is less than degree 3, so we don't have to divide. The next step is to factor the denominator. Well, if you factor out an x, you get x times x squared plus 1. And x squared plus 1 doesn't factor anymore. So when you have a rational function where the denominator involves linear and quadratic terms, for the linear term, you're going to get something a over x. And you also get a fraction with this quadratic term in the denominator, but the numerator will be linear, bx plus c. That's part of the theorem on partial fractions. So there are numbers a, b, and c that satisfy this equation. So this is, if you put this over a common denominator again, this is a times x squared plus 1, bx plus c times x over x times x squared plus 1. So this has to equal this. So when you compare the numerators, you have x squared minus 1 equals a times x squared plus 1 plus, this looks like bx squared plus cx. Now, the only obvious thing to try for x is x equals 0. So that x equals 0, these two become 0. You get minus 1 equals a. So I just found a. So a is equal to minus 1. There's no other value of x that cancels these, so you can just try some other values. Like, for example, suppose you let x equal 1. On the left-hand side, you get 1 squared minus 1, which is 0, equals, when x is 1, 2a plus b plus c. A is minus 1, so that's minus 2 plus b plus c. So we get the equation b plus c equals 2. If I say, for example, if I choose say x equal minus 1, again I get minus 1 squared minus 1, which is 0. When x is minus 1 again, this is 2a plus b minus c. And 2a is minus 2 plus b minus c. So I get b minus c is also equal to 2. And here I have two equations and two unknowns. If I add them, I get 2b equals 4, so b equals 2. And if b equals 2, c equals 0. So this expression, x squared minus 1 over x times x squared plus 1, is equal to a over x minus 1 over x plus bx plus c, that's just 2x over x squared plus 1. So we have this very beautiful identity for this function we're integrating. So we're integrating minus 1 over x dx plus the integral of 2x over x squared plus 1 dx. This is minus the log of x. And here, if you make a substitution, u equal x squared plus 1, you get the log of x squared plus 1. So that's how we do this problem.
can we go back and to where you got plus C? Like, where'd the C come from?
Sorry, where did what come from?
The C in the beginning of the problem. You got A over X plus BX plus C.
Right. So again, you have to study the section on partial fractions in the text.
Uh,
It says, this is a theorem in algebra that we're using. We're not proving it, we're using it. If you have a rational function, the denominator has larger degree than the numerator, and this denominator has degree 3, the numerator is degree 2, 3 is bigger than 2. We factor the denominator. It will factor into a product of linear and quadratic factors. Quadratic, and when I say quadratic factors, that means quadratic factors that you cannot factor into linear factors. So x cubed plus x is x times x squared plus 1, if you factor out the x. And x is linear. This is quadratic, but it doesn't factor. So we're going to get one partial fraction for each of these terms. One partial fraction with x in the denominator, one partial fraction with x squared plus 1 in the denominator. When you have a linear function in the denominator, the numerator is a constant. When you have a quadratic polynomial in the denominator, the numerator is a linear polynomial. That's what the theorem on partial fractions says. So I know from what I learned from reading section 8.5 that this function has an expansion like this. I mean, that's not something you would guess or know, it's something you learn.
all right, thank you.
Professor, what happens if they're both quadratic?
So suppose you had something like the integral of 1 over x squared plus 1 times x squared plus 2. So 1 over x squared plus 1 times x squared plus 2, these are both irreducible, they don't factor. So we'll get one partial fraction with x squared plus 1 in the denominator, another partial fraction with x squared plus 2 in the denominator, and here we'll have some linear function, and here we'll have a different linear function. But whenever the denominator is quadratic, the numerator is linear. Any other questions from homework or the review sheet that you would like me to do at this point?
Yeah, I have one.
Go ahead.
Can you do number 31 from section 7.3? I was just confused how you get the graph from the question.
7.3, number 31.
Yes.
So we have a region given by the equation x to the 1/2 plus y to the 1/2 equals some number a to the 1/2. So This only makes sense when, because you're taking square roots, x greater than or equal to 0, y greater than or equal to 0. So the graph of this is somewhere in the first quadrant. And you could have x equal a and y equals 0. Or you could have y equals a and x equals 0. And this curve is something, I don't know what it looks like, but it's going to look something like this. Because as x goes from 0 to a, y is decreasing from a down to 0. So there's going to be some region like this. And the only way I know really to get an accurate picture of what the graph looks like is to use Maple or some other graphing program on a computer or a calculator to graph it. But all you need to know for the problem is that the region looks something like this. It has to be in the first quadrant. And when x is 0, y is a. As x increases, y has to decrease, so it's a decreasing function. And when x is a, y has to be 0. So it looks like that somehow. And then you're going to be rotating this around the x-axis, around the y-axis, and around another point, the line x equal a, around that point. So that's the picture. Do you want me to set up one of the integrals as well?
You don't have to.
Okay, that's fine. All right, well, again, we have 2 problem sessions a day. So I will be here at 3 o'clock, and I welcome you to join us if you have some questions. Okay. Stay well. See you in the afternoon, perhaps.
Yeah,
Bye.
Professor. Yeah, Professor.
Yeah, go ahead.
Yeah, I just have a question, but that's not related to the work. But you know,
Go ahead.
no, I'm waiting for once people leave the chat or something.
Oh,
like that.
okay. So just so if you don't have a question for me, log out, please, and I'll have a private conversation with.
Yeah, quick question on the same one we just went over, 31.
Yeah.
So how did we know again that the line like curves like that?
Well, what I said was when x is 0, y is a. And as x gets bigger, y has to get smaller. So the function is decreasing and it has to end up here because when x is a, y is 0. So I know this is a decreasing function. I don't know exactly what this curve looks like, but it's, it could look like that. It could look like that. There are all sorts of possibilities, but in any case, it's a decreasing function.
Okay, thank you.
Thank you.
Okay. Bye. Okay.
Yeah.
Go ahead,
Okay.
sir.
Okay. Yeah, Professor. So it's just a question regarding so in the weekend. So I was just reading one of your book. So I just have a few questions if you don't mind.
So a question about what?
Your book.
Which book?
Number theory. Elementary method in number theory.
Yeah. Okay. Go ahead.
Yeah, so I was reading a few hundred pages this weekend. I found it really fascinating, especially the note part. And what I really found that was good is the fact that you had a note after the end of each chapters. But even though I wasn't familiar with a lot of mathematical symbols and all that, I kind of find it fun to look for it online, then go back reading and understanding it. And I was like, if I had read this book like when I was taking my math before I started with math, it would be really, really, really helpful for me. And like I didn't want to read the rest because I felt like this the rest, especially the one that the other books, that one I feel like is more for graduate student. But since I'm trying to go a math major, but I don't